Let's continue our discussion on common discrete distributions. The next one is hypergeometric, and we'll end this discussion with the Poisson distribution. So the hypergeometric distribution comes when you are selecting without replacement from a finite population which has two kinds of members. Marked and unmarked, but otherwise these are indistinguishable. So the question is, if we perform a sample without replacement from this population of size capital N is not a random number, it's a fixed number. The sample size is small n. So what is the probability of finding a given number of marked members in the sample? So that would be by using our definition of classical probability is in the denominator we have n choose n, and in the numerator we apply the counting principle. So we choose x from d marked members and n minus x from the n minus d unmarked members. So that ratio is the hypergeometric Pmf. And you could apply the definition of the expectation, perform the summation. The mean is the ratio of nd and capital N, and the variance is also it can be derived in terms of these parameters of the problem. Now, there's one classical problem of population estimation that can be solved using the hypergeometric distribution, and we will go through them now. So suppose there is an unknown wildlife population of size capital N. We want to estimate it, and this is the process that is followed. So we catch d of them, mark them in some manner, and then release them and give sufficient time so that these marked members mix uniformly throughout the population. Now I take a sample from this without replacement of size small n, and I find out of these x of them are marked. So I release d marked and x of them have come back. Now, what is my best estimate of the unknown capital N? There are two ways of doing this. The first one would be taking advantage of the maximum likelihood estimation. So the question, simply put, is that I have the hypergeometric Pmf, which is dependent on capital N, d and small n, but for what value of capital N is that Pmf at its highest? So we are looking for that capital N with known x, n and d, which would give me this two inequalities. So P of n would be greater than P of n plus 1 with the same parameters x, n and d, and P of n will be greater than P of n minus 1 with those same parameters x, small n and d. And now by plugging in the hypergeometric Pmf expressions and doing some algebra, we come up with two inequalities. The first one, which you see on the right, gives me one condition. The second one gives me another condition. So if you combine these two, you get a nice solution that the unknown capital N is nothing but the integer, the floor value of nd divided by x. There's also another intuitively appealing explanation of this solution, and that is by invoking the law of large numbers. It is by asserting that the sample proportion approaches the population proportion. although the underlying requirements for the law of large numbers to hold is not strictly holding here, because the samples are not strictly independent, but assuming that small n is small compared to capital N, we can still equate the two proportions, and I get the same answer for the unknown population size.